Hello, today's video is going to be about exponential parent functions. Last week we talked about exponential growth and decay, and we talked about compound interest, and those are ways that we can use exponential equations in real life, but now we're going to learn how to graph those. So the exponential parent function is f of x equals b to the x power. And b can be any number. If b is greater than 1, the function is an exponential growth and is increasing. If b is less than 1, the function is an exponential decay and is decreasing. And then the definition of an asymptote is a line which the graph gets close to but never touches. So let's start with number 1. This is an example of a parent function, and all 5 of today's examples or today's problems are going to be parent function examples. And you're going to notice a lot of similarities in their characteristics, which is what we do over here in this section. So starting with whether or not this is exponential growth or decay. B in this equation is 2, and we learned in the last slide that if b is greater than 1, that represents a function that is exponentially growing. So this is a growth function. Now I want us to go to our calculator and graph this and use the table to draw an accurate graph on here. So I'm going to show you this example on a TI-84, and then I'll show you the next example on Desmos. On our TI-84, we're going to go to the button that says y equals. We're going to click that and type in 2 to the x power. So 2, and then the caret key, which is above the division symbol. And then we use this button beside the green button for x. So 2 to the x power. And then we hit graph, which is this top right gray button. And it should look like this, but instead of just sketching the graph, we're actually going to force our calculator to show us the table so that we know exactly where these points need to go. So we're going to hit second, which is the blue button, and then graph again. Remember, that's the top right gray button to get to the table. And if we look at the negative numbers, the negative x values give us really, really tiny y values. They get very close to 0, but they're never actually going to touch 0. They're never going to equal 0 or go below. And then if you look at the positive numbers, they get really big really quickly or exponentially, which is why this is called exponential growth. So we're going to go back down to where x equals -2. This is the first point that I feel like I can graph on my graph easily because 0.25 is the y value and it is just a fourth. So we can graph that pretty easily. So let's start with -2. -2 and then 0.25. So that means from the origin, we always start at the origin whenever we're counting these. We go left 2 spots and up 1/4 of a spot or of a unit. And just get close. It doesn't have to be 100% perfect. Our next point is -1 and then 0.5. So that means we'll go left 1 and we'll go up half of a unit. And again, that is starting from the origin or where the axes cross. That very center point is where you always start. Our next point is 0, 1. So 0, 1. So we don't go left or right at all. We just go up 1. Our next point is 1, 2. So we will go right 1 and up 2. Our next point is 2, 4, so we will go right 2 and up 4. And the last point that will fit on our graph is 3, 8. So we will go right 3 and up 8. And now we're just going to put our line on here. All right, so we have graphed our function. Now we need to go through and identify all of these characteristics that it asks us for. The first characteristic we want to look at is the domain of this graph. When we look at domain, we're talking about all the x values that work for this function. So x values that we can plug in and get an answer. So the left side, x values go from left to right. So we're going to start with the left side of the function. The left side has an arrow, and that arrow points left. So it's going to go all the way to negative infinity. And then our right-hand arrow, even though it points up, it points slightly to the right. So it may take forever, but it will go toward positive infinity in the right direction. So since it goes to both infinities and there's nothing in the middle to tell us any different, our domain consists of all real numbers. Our range is the set of y values that work for this function. And if you look, y values are up and down. So the up arrow is pointing straight up. So that means it'll go to positive infinity. But the bottom arrow is kind of pointing down, but it's never going to cross 0. So our range has to be y is greater than 0 because we will never get a y value that equals 0 or less for this function. Then end behavior just wants to know what the ends of our graph are doing. The first one says as x approaches positive infinity, so that means the right side of our graph as x gets bigger in the positive direction, what is f of x doing? So we want to know on the right side of the graph, is the arrow pointing up, is it pointing down, or is it approaching a specific number? And on the right side, this arrow just points up. So that represents positive infinity in the y direction. Then we have as x approaches negative infinity, what is f of x doing? So the left side of the equation has an arrow that points kind of down, but again, it approaches 0. It's going to get really, really close to 0 and never cross it. It's not actually going to go down to infinity. So the negative infinity direction, the y value will approach 0. Now we want to know what the y-intercept is. This is the point where x equals 0, so it's always going to be 0 comma something. And then you can find this by looking at your graph, if you graphed it accurately, or you can plug 0 in for x in the original function, or you can use the table on your graph. But any of those ways, you should find that the y-intercept for this function is 0, 1. Finally, the asymptote is the line that our equation will never touch, that our function will never touch. And you can see that that's the x-axis. The equation for the x-axis is y equals 0. And now we're going to look at number 3 together. Number 2 is almost identical to number 1, so you shouldn't have any problems with it. Number 3, f of x is equal to 1/2 to the x power. First, we want to know if this is growth or decay. Our notes say that if b is less than 1, then it represents decay. So this function should be decreasing. We're going to graph it on Desmos this time so that we can see an example there. Once you pull up Desmos, you're just going to type the function in it exactly as you see it. So we have f of x is equal to 1 divided by 2 to the x power. And we can move this graph around to see the points that we want to see. Our graph only on our paper only goes to 10 on each side of the axis. So this is everything we need to see for this function. And what we can do is we can just hover over different parts of this graph Okay, never mind. I thought it worked differently than that. It does show you important points, like here at the y-intercept, it shows me that, but it's not showing me any other of points easily. So if you click in the box here, and then go to settings, go to the settings button, you can click this chart and it will give you a table. And then you can decide what X values you want in this table. So what I would do is go from -10 to +10, and then you can see which numbers you want to use. So I've extended the table all the way from -10 to +10 on the X values. So we just want to look at the Y values and see which of these we can actually use on our table. So only the Y values that are less than 10 or -10 will work. And it looks like that's going to be from -3 to, let's say, +2. I don't really want to graph anything more difficult than 1/4. So if you're sitting at home, you can plot these points on your paper while you look at your computer screen. However, for the purpose of this video, I'm going to go over and plot these, and then we'll just move on from there. I have our points plotted and our line drawn. Again, if you're at home, you can see your computer with the points and your graph at the same time. So you should be able to do that. Now we want to look at our characteristics. First is the domain, and here's a hint. It's the same for all exponential functions. So this is going to be all real numbers again. And if you notice our range on this one, everything is above the x-axis again, and the line that it gets really close to is the x-axis. So our range again is just going to be y greater than 0. But our end behavior is going to look slightly different this time because this is a decay function, so it's decreasing instead of increasing. So if we look, as x approaches positive infinity, that's where our graph goes towards 0. So our 0 is on the positive side this time. And as x approaches negative infinity, that is where our up arrow is. So the infinity goes on the negative side this time. Our y-intercept, again, is 0, 1. And our asymptote, again, is y equals 0. You're going to notice on these problems that everything except the end behavior is the same for every single problem because we are only studying parent functions today. When we talk about transformations tomorrow, that will change. But for now, these are consistent characteristics for the parent function of exponential functions. That is all for today. Thank you and have a great day.